e to the power minus pi k squared over t dx. I just completed this. Did I do this correctly? I just completed the square. So I've got to add these two. I got a quadratic in x. I wrote it like this, and then I have to remove the constant. Okay, just check my algebra. Now this part is independent of x, so this actually comes out of the integral. So this is equal to e to the minus pi k squared over t times the integral e to the minus pi t z squared dz. And I'm going to put a contour here. I can think of this as really pi t. I think of this as a z, but then the d of this is the same as dx, because this is a constant. Okay? So I'm going to think of this as a pi t z squared dz, where, this is equation 3 or something, okay? Where c is the horizontal line with imaginary part minus ik over t. I think I should say something here that we will actually, it's not a correct statement, it's x minus ik over t. I'm going to assume for now t positive, and then I will later extend it to t negative. So here's what I'm going to do. So I'm going to make a comment here. This is an analytic function in t. So I'll make a comment. Clearly, theta of t is analytic in t. So by the way, this t is not sigma plus it. Okay, this is analytic in t for t in the right half plane. So it suffices to establish the functional equation for t positive, because if this is equal to this throughout the real axis, then it must be equal by analytic continuation to identity finality functions in the entire plane, because what we're saying is this difference is now an analytic function on the right half plane. Square root of t is well defined on the right half plane, but if this function is identically 0 on the real axis, it becomes identically 0 in the entire right half plane. Analyticity. So hence, suffices to prove functional equation for t greater than 0. Real, I put real, t greater than 0. So if t is greater than 0, so that's a comment that goes in here. So if t is greater than 0, this c is a horizontal line with imaginary part. By the way, k could be negative. So this horizontal line could be above the axis or it could be below the axis.
Yeah,
Yes?
5k, there's supposed to be any t in there. Is that a t? Oh, that's a t, it's not a plus. Okay, sorry. Okay. So that's negative pi x squared t. Okay.
Yeah. So now what we're going to say is, all right, we can, so this is an integral either like this or like this. This is the real axis. So depending upon whether it's above or below the origin. But then the integral on this side, far away, goes to 0 due to the rapid decrease of the integrand. Therefore, by Cauchy's theorem, this integral is the same as the integral from minus infinity to plus infinity. Okay. So by Cauchy's theorem, okay, by Cauchy's theorem, we have phi of k is e to the minus pi k squared over t times the integral from minus infinity to plus infinity e to the minus pi t u squared du. And now this is just a real value derivative, or you can put x as a real value derivative. But now by change of variables, this is going to be equal to e to the minus pi k squared over t times a certain constant. So we'll call this constant Gauss. So it's not Euler's gamma. So I'm going to put a constant gamma. It's not Euler's gamma. I'm just honoring Gauss here. Okay. Okay. Let's put it this way. This is 1 over square root of pi t times the integral from minus infinity to plus infinity e to the minus u squared du. This is just by change of variables. Correct? That integral I call as gamma, Gauss, some constant. So e to the minus pi k squared over t square root of pi t times, maybe we call this constant g for Gauss. This is the famous Gaussian integral. All right. So that's the value of the phi k. So by your Poisson summation formula, okay, so let's give this equation 5. So by the Poisson summation formula, we have what? Theta of t is really the sum of the f's. I wrote it somewhere. Yes. Theta of t, which is the sum of the f's, must be the sum of the phi k's from minus infinity to plus infinity. And therefore, that is equal to this constant g divided by square root of pi t. I don't know what g is yet. I just know that it's a converted error. We'll get the value of g as a wash. It will just come out as a consequence of this. Okay? So it's g over this multiplied by the sum e to the power minus pi k squared over t. K from minus infinity to plus infinity. And this is valid for t greater than 0. Now, what is theta of t? Theta of t is summation e to the power minus, I'm going to put a k here instead of n. Right? So that is equal to this. Now, one thing we need to notice, if take t equal to 1 in 6, this is also part of 6. This is the value of theta of t. If I take t equal to 1, it doesn't matter whether I put t in the numerator or t in the denominator. So these two are equal. And that implies that g over square root of pi is 1. Because t is 1. Therefore, the Gaussian integral has value square root of pi. So this comes out as a consequence of this identity. But if the Gaussian integral has value square root of pi, I will cancel. So with g equal to square root of pi, equation 6 implies theorem of the functional equation. We call it a functional equation, but it's always called the transformation formula of the theta function. It's almost, it goes through two, it's very slick. When I first saw this, I didn't believe it. I had to stare at it for a while and then, sort of convince myself that everything goes through. So you get the value of the Gaussian integral automatically from this, and at the same time you get the function. This you can either call it a functional equation or it's called a transformation formula, because what is actually happening is that in the theory of partitions, this theta function is used to transform. So this is one of the key things in the Hardy-Ramanujan circle method. They were integrating they wanted to look at the partition function, generating function. We use Q there for partition series. And this is a function which has got a product representation. So this function explodes at m equal to 1. It explodes at m equal to -1. The roots are all the roots of unity. All the roots of unity of all orders. So it's kind of the natural boundary for this function in the unit circle. So what Hardy said was you can calculate P of n by computing the contour integral f of q over q to the n plus 1 dq. Okay? This is true by Cauchy's theorem over any circle. But that by itself is not going to enable one to estimate the coefficients. So what Hardy said was, let's deform this contour to come near here. We pick up the contribution here, deform the contour to go here, and deform the contour. So you deform the contour in such a way that you go near the roots of unity to pick up the contribution of the roots of unity. But how do you pick up the contribution of the root of unity? You got to do a transformation of the function from that to a value near the origin. We use this theta transformation relation. Yes.
Do you do all the roots of unity, or just ones that are sort of special, like 1, -1?
Okay, so that's the discussion I had in the review.
Right. Yes. Yeah.
So as Hardy says in his lectures, to get the main term, all you need to do is to calculate it 1, and that's pretty easy. And you can get better approximations by calculating the second root of unity and all the third roots of unity and all the fifth roots up to the kth roots. But the question is, that kind of calculation, do the error terms, are they under control or are they exploding? And Ramanujan kept saying that there is an exact formula. And so when Hardy and Ramanujan did this, they went up to the roots of unity of order, I think square root of n or something like this. And then they got the value of the partition function as the nearest integer to a remarkable sum involving exponential functions. So, and then Rademacher, by mild modification of the series, replacing exponentials by hyperbolics, converted it into an infinite convergent series. So then all the roots of unity are there. Now, this transformation is really a modular transformation for this function. But this function is related to a theta function. So that's why I'm saying these transformation formulas are coming in with the original source being the theta, and then later, of course, you modify it to more generally to modular forms. So this is a very fundamental object, and we have now going to use this to get the functional equation for the Riemann zeta function, but I need one more special function, namely the gamma function. Now in the old days, there were actually a course in most math departments on special functions. Beta function, gamma function, theta function, all of these things, and and then you discuss Bessel functions and so on, and you discuss all the properties. But again, as I said, with the more modernization of mathematics, with Bourbaki influence and so on, it's more differential geometry, algebraic topology, and so on and so forth. So there is not much time to do special functions. Although I think people in engineering and physics and so on, they are still interested in special functions. But special functions have come back into not worldwide prominence, but into prominence in some circles because of the resurrection of importance of the Ramanujan type of mathematics. So that during the latter part of the 20th century, with more and more excitement around Ramanujan center and the discovery of the last notebook, people went back and started proving identities for these special functions. So they came back into vogue after this. But when we do, of course, analytic number theory, the role of these special functions actually comes out very nice. So coming back on Monday, we will use a function equation to the theta function to establish a remarkable function.